Welcome my dear learners for this course on design of machine elements 1. In this module 1 we were discussing on stress concentration. So far we have solved 3 numerical problems on stress concentration. Let us continue our discussion. The problem number 4 of our discussion on stress concentration states that find the value of the maximum stress induced on the fillet if the stress concentration factor for the filleted flat box shown in figure 4 having a d/d ratio of 1.2. Also determine the factor of safety if the flat box is made of steel having a yield stress of 640 megapascals. So this is the given diagram for us. As we all know, we should match the given diagram between the figures 2.11 to 2.30 according to the geometric irregularity as well as the loading case. The careful observation reveals that it is an step down flat bar or stepped flat bar subjected for tension. So if I compare the figure 4 to our design data handbook, it matches with, let me discuss the solution of problem number 4. If I discuss the solution of problem number 4, the given problem matches to figure 2.16 of page number 38, that is stepped flat bar subjected for tensile loading. Stepped flat bar in tension. Now if I observe this figure, in the x-axis we have R by B ratio and in the y-axis we have theoretical stress concentration factor Kt, and here we have R by B ratio. Now if I observe the figure, he has given the ratio of d by d, which is nothing but capital B by small b according to our convention, referring to design data handbook written by K. Madhavan and K. Balavira Reddy. We are referring 4th edition. So therefore the data given for us is nothing but d by d. According to our convention, it is capital B by small b, which is equal to 1.2 given. So this is given for us, no problem. Now if you carefully observe the figure 4, capital B to small b is known, whereas capital B minus small b is 2 times the radius. This is the capital B and this is small b. If I remove that, I will get 2 times the radius. That is from figure 4, that is from the given figure, I can write it as capital B minus small b. This is capital B minus small b is equal to 2r, is equal to 2 times the radius. So therefore I can write it as, how much it will turn out to be? It will turn out to be capital B minus small b is equal to 20. This is one equation we have, and we have one more given equation. Therefore I can write it as b is equal to 1.2b, or I can write it as b minus 1.2b is equal to 0. Correct? From this equation I can write b is equal to 1.2b, rearranging it, b minus 1.2b is equal to 0. That is b minus 1.2b is equal to 0 from the given data. So if I solve by using equations with 2 unknowns, we have coefficients as 1, minus 1, 20, 1, minus 1.2, 0. So the value of capital B is turning out to be, on solving these 2 equations, I will get the value of capital B as 120 millimeters and small b as 100 millimeters. 100 millimeters. Now I can find R by B. So therefore R by B ratio will be 10 by 100, which is equal to 0.1. Yes. So mark 0.1 here, and here we have the curves of capital B by small b. It is given for us, it is 1.2. So therefore choose the curve of capital B by small b is equal to 1.2. Capital B by small b is equal to 1.2. Move ahead, intersect this, and from the intersection of b by b 1.2 come horizontally towards left, and you will find that stress concentration factor is found to be 1.8. Stress concentration factor is found to be 1.8. So now I know stress concentration factor as 1.8. So therefore we know that from definition Kt is equal to sigma max by sigma nominal. Sigma max by sigma nominal. He has specified the value of, he has not specified the value of sigma max. He is asking us to find the value of sigma max. So therefore find sigma nominal also, that is sigma nominal for tensile stress is given by load by area, that is F by A, whereas area is given in the figure 2.16 itself as T into B, thickness into small b. Small b is found to be 100 mm. So if I substitute and solve, I will get the value of sigma nominal as 120 into 10 to the power of 3 divided by thickness is 25 mm into b is 100 mm, because in the figure 2.16 they have specified that area should be taken as thickness times small b. In the figure 2.16 page number 38. So I taken that, hence I will get the value of sigma nominal as 120 into 10 to the power of 3 divided by 25 into 100, that is 48 megapascals. Now I can find what is the value of sigma max. Now sigma max is equal to stress concentration factor times sigma nominal, hence I will get the value as 48 into 1.8. 48 into 1.8 is turning out to be 86.4 megapascals. So we have found out the value of Kt as 1.8, referring to figure 2.16 page number 38. And he is also asking us to determine factor of safety if the flat box is made of steel having an yield stress of 640 megapascals. So we know that the formula for sigma max when yield strength is known is given by sigma max is equal to sigma yield by factor of safety. So therefore factor of safety n will become sigma yield is 640 divided by allowable maximum stress is 86.4, hence the factor of safety is turning out to be 640 by 86.4, that is 7.407 is the factor of safety. This is the complete solution for problem number 4. Let us move for solution of problem number 5, which states that find the diameter of the hole in the figure 5 if the stress concentration factor at the hole is to be same as that the fillet. Now if you carefully observe, this is also a flat bar with hole at center and also a flat stepped bar. We have a fillet radius of 5 mm. First what we do, as he said, stress concentration factor at the hole is to be same as that of fillet. First find out what is the stress concentration factor using the fillet section. Use the same value for hole section and find out what is the diameter of the hole. So therefore if I move for solution of problem number 5, that is, now if I compare the fillet section, considering fillet section, fillet section, we can compare this section to figure 2.16 referring to page 38. Referring to page 38, we'll have, this should be tension, make it as tension. It is stepped bar in tension. Take it as tension. That is stepped flat bar in tension. Stepped flat bar in tension. Now if I compare that figure, on the x-axis we have R by B. We know the value R by B is given as 5 by 50, which is 0.1, and y-axis is theoretical stress concentration factor Kt, and we have the curves of capital B by small b. That is capital B by small b for this problem will be 85 by 50. 85 by 50, which is nothing but 1.7. But in the graph, if you observe, you have the curves only for 1.5 and 2. You have curves only for 1.5 and 2. So take 0.1 and take close to 1.2 or exactly in between, because 1.7 lies between 1.5 and 1.2. Exact center is 1.75. So take it at the center and project it horizontally. If you do that, you get stress concentration factor as 2.18. You get stress concentration factor as 2.18. 2.18. So therefore, you will get Kt is equal to 2.18. Now he says that the stress concentration factor at hole is to be same as that of fillet. Hence, if I consider the hole, that is considering the section whole section, it is flat bar with a hole subjected for tensile loading, that is from figure 2.12 referring to page 36. Referring to page 36, you have x-axis as A by B, that is hole diameter by width 85 mm, and we have a curve, simple curve, and y-axis as stress concentration factor Kt. This is for figure 2.12, page number 36, flat bar with a hole subjected for tension, that is flat bar with hole in tension. Now we know stress concentration factor, that is 2.18. So mark 2.18, take horizontal line, intersect this curve and come vertically downwards. It is exactly opposite what we were doing earlier, and you will get the value of A by B as 0.5. So therefore we will get the value of A by B as 0.5. Now we know what is the value of capital B, that is 85. Hence the hole diameter will be A is equal to 0.5 times 85, hence the hole diameter will be 0.5 times 85, which is turning out to be 42.5 millimeters, 42.5 mm. So this is the solution for problem number 4 and problem number 5, wherein which we have addressed stepped flat bar subjected for tensile loading. That's all from this lecture. Thank you all.